Okay, welcome everybody. So we're just doing the last bits of material this week. We're going to cover section 10.2, which is solving exponential and logarithmic equations. So we're going to use what we learned about logarithms to solve equations. All right. Before we do that, I want to just point out that the final exam I have scheduled for Thursday, May 21st, okay? And you can start it at any time between 10 a.m. and 8 p.m., just like the last exam. Be very similar to the last exam, but it will cover it'll cover little bits of all the material that we've covered since day one, okay? There's a lot of material there, but if you look through the homeworks that we had, those are the kinds of things, any one of those problems could appear. I've posted those old exams. You can find them on MyOpenMath. I believe I did. Let me check. Or I'll take you there with me, and we can go have a look. Okay, so you should see this when you go to MyOpenMath. And you can see a review for exam 1. I posted those homeworks there, so you can review those assignments. Review for exam 2. You'll even see exam 2 there, and if you click it, you can see the solutions to the exam problems, and then the homework problems that were used for that exam. And then review for exam 3. That exam is there as well with the solutions and homework for that exam. Okay. As these homeworks in chapter 10 expire, I'll post review versions of them as well, so that you can review chapter 10, and there'll be a section coming up here for that. But it'll cover everything. I think I have a review sheet that I'll upload for you. Okay, so you can take a look at that and kind of guide you with maybe the problems that you may want to focus on more than others. And I'll post that this week. And then on Thursday this week, we won't have new material. I'll just be here to answer questions. So that's the plan. So if you've got questions, I'll be happy to answer them. If not, I have no new material to discuss. So it'll all be up to you whether you have things to ask about. Keep in mind, you can check your grade in the grade book here, and look through your exams, the comments that I've left. You'll see in the grade book if any comments were left next to your exam score. Okay. Okay. So we will, like I said, we'll finish covering chapter 10 today, and I see some questions about different problems in chapter 10 are coming in. The question about 10.2 number 19, and then 10.4 number 19. Okay, so I'm going to review some of chapter 10.4, so maybe that'll clarify what's being asked there, and we'll take a look back at that. But let's go look at 10.2 number 19. Okay, so here we are. Let me zoom in a little bit. Number 19, the very last question. Okay, so I'm going to write this one down, and we'll go to the paper to take a look at this more closely. All right, should be seeing my paper here. So what were we being asked? I wrote down the equation. What do we do with it? It says solve. Okay, so we have to solve this thing for x. All right. Well, what did we have in, excuse me, in section 10.2 to solve things? We had the one-to-one property. We had the one-to-one property of exponential functions. The one-to-one property says that if b to the x equals b to the y, that means that x equals y. It works the other way too, of course. If x equals y, then of course these things would be equal. But the one-to-one property says it goes both ways here. So this is something we can use to solve this equation. Exponential functions aren't the only functions that satisfy the one-to-one property. Other functions have this property as well, but not all functions. So it's a special property enjoyed by some functions, but not all. But we can use it here. So the only thing is, in order to use this property, we need the same base on both sides of the equal sign. I don't have that here. I've got a different number on the left than on the right. So the idea is that if we're going to use this one-to-one property, then we are going to need to rewrite this so that they do have the same base. Okay? What base do you think that I can get them both to have? Well, 125 ends in a 5. That makes me think it's a power of 5. And so if we think 5 squared is 25, and if I multiply 25 times 5, I get 125. So 125 is 5 cubed. Okay, so we can write the right-hand side as 5 cubed to the x plus 2. And the left-hand side ends in 5 as well, so it might also be a power of 5. In fact, 625 is 5 to the 4th power. So I can write that as 5 to the 4th to the x plus 4. So it looks like I might be able to get the base to be 5 here. All right, but the bases are still different. I got 5 to the 4th, 5 cubed. These are not the same b. So I got to do a little bit of manipulation here. Well, I can use properties of exponents. I know that when I raise something to a power and then raise that to a power, what do I do with the exponents? Multiply them. So this is the same as 5 to the 4 times x plus 4. And same thing here, I multiply these. So this is 5 to the 3 times x plus 2. And look what I've got here. Now the bases are the same. So I can use the one-to-one property, which says that if the bases are the same, then the exponents must be the same. So this tells us that, I'll have to write it down here, 4 times x plus 4 equals 3 times x plus 2. And I think you can solve this the rest of the way. Right? So you can take it from here. Because now we've just got it down to a simple algebra problem. So that's how you do a problem like this. You've got to get the bases to be the same. And then once you do, you can use the one-to-one property. Okay? Are you always going to be able to do that? I mean, if I wrote 2 random numbers here, no. All right, so these are special numbers that happened to both be powers of 5. But fortunately they were, so we can do this. Okay. What do you do if they weren't the same base? Well, that's what we're going to talk about in the section that we'll cover today, section 10.4. Okay. There's another question, 10.4, number 19. Before I take you over there, I just want to take a look at it because I want to see if it's something that I should discuss now or maybe after we talk about some other things. Oh, there is no 19 in section 10.4. So update your chat and let me know what you meant. Maybe you meant number 9, but you know, Aisha, if you want to update that, because I'm looking at section 10.4 and it only goes from numbers 1 through 10. So I'm going to start reviewing some of this stuff, and we'll go and explore some of this newer stuff. Oh boy. Almost lost my notes. Okay. So, yeah, where were we? We talked about section 10.2 exponential functions. Then we did, and that's what we just did here in that example. And then we talked about logarithmic functions. Let me quickly just go over those. Okay, so exponential functions in 10.2. These are functions of the form b to the x, where b is positive and b is not equal to 1. Okay, that's an exponential function. Okay, so things like 5 to the x, or 10 to the x, or pi to the x, or e to the x, that's the natural exponential function, we call it. So all these things, you could have fractions, 1/2 to the x. Can't have a negative number or a number equal to 1, though. Okay, those are exponential functions. So we talked about those, and we talked about their graphs. We talked about how the graph of an exponential function will either look like this if b is positive, or it'll look like this if b is negative. Oh, sorry. Sorry. B can't be negative, right? I meant it'll look like this if b is greater than 1, and it'll look like this if b is less than 1. Okay? And they have a nice property that they always cross the y-axis at the same point. That's the point 0, 1. Okay? And there were some homework problems that required you to graph these. So typically by graphing them, you'll plot one point, you get that one for free, right? That's always going to be that point, the y-intercept. And then another point you can just get by plugging in a number. So plug in 1 for x. If you plug in 1 for x, say 5 to the x, you just get 5 to the 1, that's just 5. So that would tell you, so if I take the number 1 and get 5 as an answer, now I know I have another point on that graph, right? So I know I have, this must be 5 to the x, right, if it goes to this point. So that's an easy way to graph, is just by plugging in 1 for x. Or maybe -1 for x if it's a fraction or something. And then you can graph these easily. But they look like this. They have a horizontal asymptote equal to the x-axis. Okay. We also talked about, in the next section, logarithmic functions. Okay. So 10.3, logarithmic functions. Okay, logarithmic functions are related to exponential functions. They're actually what we call inverses of one another. Just like square root is the inverse of x squared, or x, cubed root is the inverse of x cubed, the logarithm is the inverse of the exponential function. So logarithmic functions we write like this. And they take a little bit of getting used to, so they take some practice getting used to. And we went through a bunch of practice problems in the last video. And again, since they come from exponential functions, the b satisfies the same properties. B is positive, and b is not equal to 1. Okay? And what do we do for exponentials? We just looked at some examples, right? So let's do that. So you might have like log base 2 of x. That's an exponential function. Log base 10 of x, we just write log x. Log base e of x, we write ln of x. Okay. And what do these look like if we were to draw their graphs? Well, their graphs come in 2 varieties as well. They will either look like this or like this. And they always cross at the point 1, 0. After all, the graph is just the graph of the exponential function turned sideways, because they're inverses, and that's what happens with inverse functions. I should label my axes here just to be extra clear here. And what we're doing is we're graphing y equals log base b of x. Okay. Which gives us this graph and what gives us this graph? Well, again, that has to do with b. This happens if b is greater than 1. This is the picture you get when b is less than 1. Okay, so we have 2 different pictures depending on the value of b. Okay, so those are the logarithmic functions. Because logarithmic functions are the inverse of exponential functions, when I plug one into the other, they cancel each other out. Just like if I take the cubed root of x cubed, I get x. Or if I take the cube of the cubed root of x, I get x. If I plug one function, if I plug the inverse into a function, the inverse of a function into the function, I just get x back. Same thing happens with logs and exponential functions. And that brings us to some of the first properties of logarithms that we discussed. Okay, so let's take a look at some properties of logarithms. And that's section 10.3, which we just touched on at the end. Wait, where are we now? Properties. Oh, it's 10.4, sorry. I thought I was off. Properties of logarithms. And that property that I just said is the inverse property of logarithms. The inverse property says that if I take an exponential function and as the exponent put a log of the same base, what do I get? Well, we just said it, we get x back. In other words, these things can be thought of as canceling each other out. Just like if I take the cubed root of x cubed, what do I get? I get x. Right? They cancel each other out. And it works the other way too. If I take the log and I plug in the exponential function with the same base, these bases have to be the same number. Right? These have to be the same. What do I get? Again, x. Right? Just like if I took the cubed root of x and cubed it, I would get x. Same thing. They're inverse functions, so that's how they behave. They cancel each other out. So that's a wonderful property that we're going to use to solve logarithmic equations. So, or exponential equations as well. If we want to get the exponent, so look what happened. I had an exponent, and now it's not an exponent. So if I've got to pull that exponent down, I can use this to do that. All right. We talked about some other properties of logarithms. Before we go in and solve equations, let's just talk about some of the other properties. We talked about the product property, the quotient property, and the power property of logarithms. Instead of writing all these down, I'm going to point you to the book here, okay? Because we wrote them down last time, so why tire out my poor hand that's been writing all day? So let's go to the book here. I want to show you, it's worth pointing this out anyway, that there's a nice little table here where they summarize all this. So here I am in chapter 10.4. And scrolling down, I saw some properties go by. There's the power property. But after all those, we come to this. Look, they've summarized all the properties right here. That's pretty handy. So on this, in section 10.4 of the book, they've got all these different properties. Some of them don't have names. There's just the property that if you take the log of 1, you get 0. If you take the log of the base, you get 1. And then we have the inverse property that we just discussed. Right? And they do it in terms of log base, any base, and then also in terms of the natural log. And they do it because the natural log they do it separately. It's the same thing. It's just that they're doing it separately because it does have a different way of writing it. So just in case people get confused, they're expressing things in terms of the natural logarithm and the natural exponential function. And here's the ones that I was about to talk about. The product property of logarithms. The log of a product, here we have a product, m times n, is the sum of the logs. Look at that. A product becomes a sum when you take a log. And that has to do with exponents. When I multiply two exponential functions together, I know I add their exponents. That's why this is happening, because remember, the log is giving you the exponent. Here's the quotient property for logarithms. Quotient means divide. And so when it tells you how to take the log of a quotient. It says the log of a quotient is the difference of the logs. Well, that's pretty cool. And that should be familiar to you from exponents as well. When I divide two exponential functions with the same base, I subtract their exponents. Well, that's what's going on here, because the log is the exponent. It gives you the exponent back. And then we have the power property of logarithms. The power property of logarithms says that the log of something to a power is the power times the logarithm. It's the power times the logarithm. And that is also related to exponents. When I raise something to a power and raise that to a power, like the first example we did today, I multiply the exponents. That's what's happening here. So these are really nice properties of logarithms. And again, in the right column here, they're just expressing the exact same things. Everything's in terms of log base e, right? The natural log. We write that ln, which mathematicians almost always just use natural log. They don't even use the other ones. So what I want to do is I want to go through some examples where we use these properties to expand expressions. And that's what's going on here. I have a concise expression here, and I've expanded it to the sum of logs. Or I've expanded this quotient to a difference of logs. Right? So we want to do that with some expressions, okay? So let's go back to the paper, and I got some examples ready for you. And are we seeing the paper? Yeah. Okay. If you ever aren't seeing what you think you're supposed to be seeing, let me know. That happened in my last class. I was going on for 10 minutes and I didn't realize my students couldn't see my paper. That's not good. So, so let me know. Expand. These are just like the homework problems you'll be seeing in section 10.4. A lot of problems that ask you to do things like this. So let's start with something very basic. Log base 2 of 6 times a. Okay, so here we have the log of a product. It's 6 times a. So I know how to expand that. I use the product property. The product property says this is the log base 2 of 6 plus the log base 2 of a. That's the product property. And I've expanded it. I've applied the properties of logarithms to write a product as a sum. Okay, so done. Let's try another one. Log of 10x. What would I do here? Well, again, it's a product, 10 times x. So I'll write this as log 10 plus log x. Now this one, I can do a little bit more. I can go one more step, right? You see why? This is log base 10. When I don't write a base, it's implied that it's base 10. All right, just like in the square root. If I don't write an index, it's implied that it's the square root. It's implied. And that's the same thing here. When I don't write a base, it's implied that this is log base 10. But we know that log base 10 of 10 is, if you don't know, go back to those properties. Let me take you back there. Right here. Look, log base a of a is 1. So log base 10 of 10 is 1. Right? So that's what this is. This is just 1. So a better way to write this would be 1 plus log x, because we should always simplify if we can. Okay, so apply the property and then simplify if you can. Let's do another one. Let me do another one with, let's do log base 3 of 9y. Well, I would write this as log base 3 of 9 plus log base 3y. Can I do a little bit more? I can. Log base 3 of 9 can be simplified. Remember what log is. Log is the exponent that you would put on the base to get this number. So what exponent would I put on 3 that would give me 9? Well, the answer is 2. 3 squared is 9. So this is equal to 2. That worked up here too. I'd be asking, what is the exponent that I'd put on 10 to get 10? Well, 10 to the 1 equals 10. That's why it's equal to 1. So again, we can simplify like this. And we did a bunch of problems like this last time where we simplified things that just look just like that. Right?
What happens if the number was a negative?
If the number was negative, well, okay. Neither of these can be negative. All right. Remember, the base is not allowed to be negative. It's always positive, not equal to 1. And if you remember the graph of the log function, look at its domain. The domain is the set of x values for which it's defined. Okay. It's not defined over here. It's not defined for negative x. So it doesn't make sense to plug in a negative number for x. Same thing even if the base is less than 1. It's not defined over here for negative values of x. So if anybody ever asks you to compute log base b of negative, what you would write is does not exist.
Oh, okay.
Turns out if you use complex numbers, you can actually make sense of this. You know, like you can make sense of the square root of negative 1. You can kind of make sense of this too, but we're not doing that. So don't worry about that. This does not exist for us. It's not a real number.
Okay.
That's a good question because, yeah, I mean, that's what would happen. I'm glad you're asking. Let's do another one. Log base 4 of 3/4. What would that be? Well, here we have a quotient. So we'll use the quotient rule. Right? So what does the quotient rule say? It says that, oh boy, let me put I just realized if I do this and then do this, I'm trying to get I'm looking at my screen on my phone and I'm realizing I'm seeing my paper and then another picture of the paper off to the side. It wouldn't hurt if you could see my face there. Do this. I don't know. Anyway, you're seeing the paper. That's what's important. Okay, so I messed it up. shouldn't have toyed with it. Okay, anyway. Okay, let's do this. You've had time to think it through. Maybe you solved it. This is going to be log base 4 of 3 minus log base 4 of 4. Because that's what the quotient rule says. Quotient rule says we subtract when we divide. Now, can I simplify this? Well, I can't simplify the first one. There's no nice integer or anything that I could put on as an exponent of 4 to get 3. So that's just going to have to stay. But I can do this one, right? Just like this. Log base b of b is 1, right? So log base 4 of 4 is 1. So I can write it like this. So that's how you use the quotient rule. What about that power rule? Let's do a natural log this time. So the natural log of 5 to the 4th. Well, the power rule said that you bring the power down in front. It turns into multiplication. So this one would become 4 times the natural log of 5. That's how we apply the power rule to expand this. And so the power comes out front. Okay. This would be a case where you would be allowed to have a negative. So let me maybe point that out. Log base 5 of x to the negative 3. That's okay. The exponent can be negative. And what would I do? I'd pull the negative out in front. Negative 3 times the log base 5 of x. Right? Again, just using the power rule. Because just because the exponent's negative doesn't mean the result is negative. Right? Raising something to a negative power doesn't make it negative. So this is okay. We can string more than one thing together here, more than two things together, rather. Let's do this. Log base 3 of 5 times x to the 6, y squared. Well, what have we got in here? We got a product. Okay. So that means that we can use the product rule, which means we can write this as a sum. Log base 3 of 5 plus log base 3 of x to the 6 plus log base 3 of y squared. But I'm not done, because I can use the power rule on these. Right? So I can go another step. Nothing I can do with this one. But I can do something here. I can bring the exponent down in front. I can write that as a product. And I can write this as a product. Check that out. So there we fully expanded it. Just using the product and the power rules together. Okay. I'm going to leave that one on here, but move down on the new sheet. Okay. What if I did log base, I don't know, 8 of, let's do the 5th root of 3x. What would happen there? Well, what do I have in here? I've got 3x and a 5th root. How can I write that in such a way that I can use one of our properties? Well, you can write a root as an exponent, right? Every root is it's just notation for an exponent. It's a different notation. I can write this as log base 8 of 3x to the power 1 over 5. Right? The 5th root is the same as the 1/5 power. And now I can use that property, right? The power property says I can bring that 1/5 down in front. But I'm not done, because I can still expand this more, right? Because that's a product. So this is going to be 1/5 times a sum, right? Because the product property says this becomes a sum. And that's as far as I can go. You might distribute the 1/5 through, you might not. I don't think it matters. If they wanted you to, you should know that you can do that, but I don't think it'll be necessary. Okay, so that's how we can handle roots. Let's check this one out. Let's make it a little bit messier. Log base 4 of the cubed root of x to the 4th divided by 2y cubed z squared. Look at this mess. Let's simplify this. Okay, same thing I did before. That cubed root can be written as an exponent. That's the same thing as log base 4 of stuff raised to the 1/3 power. And because it's a power inside a log, I can pull the power out front. So that's the same as this. So that's using the power property. Just bring the exponent in front. Now, what do I have next? I've got a quotient. So I can use the quotient property. So this is going to be 1/3 times a difference. Log base 4 of x to the 4th minus log base 4 of 2y cubed z squared, because that was my denominator. So that's the quotient property. So we use the power property. Oh, I better not use P for power because the product also starts with a P. Power property. Here's the quotient property. Go from here to here. And now what can I do? Well, here I can use the power property again. I can pull that 4 out front. I'm going to need more room over here. Move, scooch to the left. Okay, so, there we go. So I pulled that power in front using the power property. What can I do here? Well, that's going to become a sum because it's a product. So what I'm subtracting in here is going to become a sum of things. And there's 3 things. Right? So I'm going to have log base 4 of 2, log base 4 of y cubed, and log base 4 of z squared. And now I can still do more because now we have powers in here. So I can pull the powers out front, right? So the log base 4 of 2, nothing I can do with that. Well, actually there is, well, is there something? I'll let you think about that. Can I simplify this? Think if I could simplify that. What about this one? The power comes out front. Same with this one, the power comes out front. And let's see if you figured out what we can do here. Remember what log of a number is. It's the exponent I would put on the base to get that number. So what exponent would I put on 4 to get 2? Well, 2 is the square root of 4. So the exponent would be 1/2. So this is the same as 1/2. Okay. So let's see what's going to happen. I'm going to subtract 1/2. Then I'm subtracting 3 log base 4 of y. And I'm also subtracting 2 log 4 of z. Whew. There we go. I think I'll just leave it like that. You could distribute the 1/3 through, but then I'm just going to get more fractions. I mean, that'll not be a fraction anymore because the 1/3 and the 3 will cancel out. But I'm going to get a fraction here and here, so I don't know if it's worth it. So I'll just leave it like this. Okay. So that took a lot of steps, right? But you just take one step at a time. Just keep looking through those properties and asking yourself, can I can I apply one of these properties to what I've got? I mean, if the thing inside the log is a quotient or a product or something raised to a power, then yeah, you can do it. And then when you get it down to numbers, ask yourself, can I find a nice rational number that would denote that, right? If you can, go ahead and write that down. If you can't, just leave it as a logarithm. You know, like we left over here, log base 8 of 3. There's no nice way to simplify this, so I would just leave it log base 8 of 3. I wouldn't write it as a decimal, because if you write it as a decimal, you're going to have to round, and then you're approximating, and it's better to write an exact answer. Better to write an exact answer than to approximate. Okay. Let the person who needs to use the number to, I don't know, let the engineer who's building the bridge do the approximations, right? You don't want to be the one blamed for rounding incorrectly, right? So, okay, so that's properties. That's using those properties of logarithms. Okay. So that's it for section 10.4. So we're going to go into the last section here, 10.5, and we're going to talk about solving equations. All right, we're going to use all this stuff to solve equations. All right. And the first thing that we're going to do solving logarithmic and exponential equations. The first thing that we're going to do is we're going to talk about the one-to-one property again for logarithms. Turns out if a function satisfies the one-to-one property, so does its inverse. All right. So the one-to-one property for logs. All right. What's the one-to-one property? It says that if log base b of x equals log base b of y, that's true if and only if x equals y. Just like it's the same property that we had for exponents. Don't know where I put that in my notes, but I hope you remember it. Oh, there it is. Right, same idea. If the two functions are equal, then the inputs must have been equal. Okay. So this is going to help us solve logarithmic equations. So let's see how this will work. Okay. Let's take a look at this one. Solve. Two log base 3 of x equals log base 3 of 36. Well, I don't yet have it in this form, right? Because I've got a 2 out front. So let's fix it. Let's get that 2 out of being out front. So what can I do to get that 2 out of there? Well, I can use one of the properties of logarithms in reverse. What property of logarithms would put a 2 over here? It's the power property. The power property brings the exponent down in front of the log. So just use that property backwards, and we can write it like this. Write it back as an exponent. If I use the power property, I'd go from here to here, but I could just do backwards and come to here. And now I've got that the log base 3 of one thing equals log base 3 of another thing. So by the one-to-one property, we know that these two things must be equal. Okay? So x squared must equal 36. And that's the one-to-one property. That's pretty nice. And now I can just solve this, right? If x squared equals 36, that means x equals plus or minus 6. The square root, plus or minus the square root of 36. Now here's where we have to be careful, okay? we need to make sure that we didn't pick up, remember, extraneous solutions can happen. Sometimes in the methods that we use, especially when you deal with squares, the mathematical methods you use to get to a solution might lead to values that aren't actually solutions. Okay, we've got the solution here, but did we pick up something extra? Well, let's check these. When x is positive 6, okay, let's check x equals positive 6. Well, I plug that in up here. 2 log base 3 of positive 6. That makes sense. There's nothing wrong with that. It's in the domain of log, everything's fine. All right? So that's fine. However, if I check x equals negative 6, and I look at where there's an x up here, what's wrong with that? Well, remember, and this is why I'm glad that somebody asked earlier about what if one of the numbers is negative. Well, I mentioned that they can't be negative, right? Because negative numbers aren't in the domain of the log function. Negative numbers are over here, but there's no graph over there. The function doesn't take those values as inputs. So that's not in the domain, so this does not exist. So how can this equation be true if this doesn't even exist? It can't be true. The right-hand side exists, that's fine, but the left-hand side doesn't, so that can't work. So that means that x equals minus 6 is not a solution. This is called an extraneous solution. It's a number that comes about through this problem-solving method, but that's not a solution to the original problem. All right, so we rule out x equals negative 6. So really the only solution here is x equals 6. So always check your answers. All right, it's not always going to be the case that one of them is not going to work, but it could be, and this is an example of that. Okay, let's do another one. Let's try this. We want to solve for x. Okay. Well, what can we do here? Well, what did we do in the last problem? We used one of the properties backwards. Maybe we can do the same thing. What property resulted in a sum? It was the product property. So this is the same as the log of a product, because right now I've got a sum of logs. Right? So I can write this as a log of a product. What's the product? It's this times this. All right. Now, if I'm going to use the one-to-one property, I would write the right-hand side as the log of something. Okay, so that's one way to think about this, right? So you could, I'm not going to do it this way, but you could write 3 as the log base 2 of, now you got to think, log base 2 of what equals 3? Well, 3 would be the exponent on 2, so that would be 8. So I could write log base 2 of 8 over here. Okay, but I'm just going to leave it at 3 because I'm going to think about this slightly a different way. Just when I see this equation, I should know that if I say the log base 2 of something equals 3, that 3 is the exponent on 2 that gives that thing. That's how logs work. The log, which is 3, equals 3. That's the exponent on the base that gives this. So in other words, x times x minus 2 equals 2 cubed. So x squared minus 2x equals 8. If I had just plugged in log base 2 of 8 over here and used the 1-to-1 property, I also would have gotten to here. So I could have used, could use this right there, or you could do it the way that I just did it right here. There's kind of two options, okay? But now we got down to an equation that we can now solve for x. This is a polynomial equation, so you know there's several methods. You could complete the square. You could use the quadratic formula. Let's just factor it. I mean, if you could factor it, I think that's the best thing to do. Subtract 8 from both sides. Let's see if we can factor this. Looking for two factors of -8 that sum to -2. What about -4 and +2? Yeah, if I multiply this out, I get this. Okay, so I'm getting two solutions. I get x equals 4 and x equals -2. All right. So now which, let me not write it that way. That might be confusing. Let me use an or. We should check these and see if either of these are extraneous solutions. All right. So if I check -2, does it work up here? Does it make sense? Can I take log base 2 of -2? No, I can't. I can't take the log of a negative number. So this is my extraneous solution. Can I take log base 2 of 4? Yeah, totally. I know what the answer is too. It's 2, right? And then if I plug 4 here, I have a 2 on the inside. Log base 2 of 2, that makes sense. It's 1, and yeah, 2 plus 1 is 3. I can see that the equation really is satisfied. So the solution is x equals 4. We did have an extraneous solution. Don't think that the -1 is always going to be the extraneous solution. We can arrange these problems so that the -1 works, okay? And it can actually be the case that the +1 is the extraneous solution. So make sure you check these carefully, okay? Don't just assume that the -1 is going to be the one with the problem. If I wrote 2 minus x instead of x minus 2 here, everything would have been flopped around. Right? I'd have to change this too, but you can arrange that. All right. Let's look at another one. Maybe I need another sheet here. Let's do one with a difference of logs. Okay. We're going to solve here. I'm just writing log, so that means log base 10. So we want to solve this for x. Okay, well, we're going to use properties of logarithms here. What property will I be using? Well, which property gave me a difference? See, I have a difference. Subtraction. Well, that was the quotient property. So I should be able to write this as the log of a quotient. So that's what I'm going to do. I'm going to write this as log of something divided by something else. It's going to be x plus 2 divided by 4x plus 3. Okay. And what about the right-hand side? Okay, I don't want this minus sign to be here. The 1-to-1 property for logarithms does not allow a negative sign to be out front. So I need to somehow deal with that. Okay, how do I deal with that? Well, I can view a negative sign as multiplying by -1. Same thing. Putting a negative sign on something is the same as multiplying it by -1. And if I multiply by a number, I can use the power property to bring that up as an exponent. So I can write it like this. Okay, so now I've got it in the form, well, where I can use the one-to-one property. If I have the log of something equals the log of something else, then those things must be the same. So I know that x plus 2 over 4x plus 3 must equal x to the negative 1. Which, by the way, is the same as saying 1 over x, right? So just think about this equation. That's what I have to solve. How do I solve that equation? Well, I would multiply both sides by the least common multiple of these quantities. All right, so what I'm going to do is I'm going to take that equation. I'm going to multiply both sides by x times 4x plus 3. Okay, so the x's cancel here. The 4x plus 3 cancels here. And what do I get? I get x times x plus 2 equals 1 times 4x plus 3. Okay, well that's looking better. I've got a polynomial now, so let's multiply it out. Let's collect everything on the left-hand side. Maybe we can factor this. Let's see. So I'm going to subtract 4x from both sides. I'm also going to subtract 3 from both sides. All right, so x squared plus 2x minus 4x leaves me with a net minus 2x. Minus 3 equals 0. So now I got to factor this. I'm looking for two factors of negative 3 that add to negative 2. Let's see. Factors of negative 3 that add to negative 2. How about negative 3 and positive 1? So I'm getting two solutions here. The thing that makes this 0 is x equals 3. The thing that makes this 0 is x equals negative 1. So I got two solutions. I got to go back and check them. Okay. Let's see. Let's check 3. See if it works. Can I do log of 5? Yes. Can I do log of 4 times 3 plus 3? Yeah, that's a positive number. Can I do log of 3? Yeah. So 3 is good. That's part of my solution. Okay. What about negative 1? Can I do log, if I plug negative 1 over here, does it work? Well, yeah, because negative 1 plus 2 is positive 1. And I could take log of positive 1, no problem. So negative 1 works fine here. Can I put it here? Negative 1 times 4 is negative 4, plus 3 is negative 1. Now I have a negative inside the log. That does not work. That is not defined. So I have to exclude negative 1 from my solution set. So the answer here is just x equals 3. This is an extraneous solution. Okay. But like I said, it's not always going to be the negative 1 that doesn't work. So we're just using this one-to-one property or any other property of logs that you can use to get rid of the logarithm to turn this into an algebraic equation. Okay. Okay. So we have one thing left to do, and that is we're going to solve, if you remember the title of this section was solving logarithmic and exponential equations. So let's see if we can solve an exponential equation. Two to the x equals 3. Well, I can't use the one-to-one property of exponents here. That's not going to do it because these don't have the same base. So that's not going to work. If they had the same base, I could do that, but they don't. So what can I do? Well, we can use logarithms here. The idea here is that if we take the log of both sides, then we can pull that exponent out front. And then we have a hope of solving for it. So what I'm doing here is I'm using the one-to-one property the other way. So instead of going from left to right, I'm going to take an equation, x equals y, and just apply a log to both sides. So we can go this way too. Right? So what we're going to do is we're going to take the log of both sides of this. We have to choose a base for our logarithm. Well, since the base here is 2, why don't we use log base 2? So I applied the log of to both sides. Now what happens here? What's the log base 2 of 2 to the x? It's the exponent that you'd put on 2 to get 2 to the x. Well, that's x. Or, thinking about it another way, that was the inverse property of logarithms, one of the very first things we wrote down today. Remember that if the bases are the same, these just cancel each other off. And I got my answer. I'm done. That was easy. I solved for x. I can't simplify this, so I just leave it like this. Okay. Let's do another one. Let's do 2e to the x minus 5 equals 18. Remember, e is that number 2.71828 ... It's just this irrational number. Doesn't really matter. We can use logarithms to solve this. What I want to do first, though, is get rid of the 2 that's in front. So the first thing we do, let's divide both sides by 2. Okay. So I'm going to divide by 2 here. Now, what logarithm should I use? Well, I'd like the base to match this. All right, so I should use log base e. What do we call log base e? We call it natural log, or ln. So what I'm going to do is take ln of both sides. All right, well, from the inverse properties of logarithms, these cancel off, so I'm just left with x minus 5 over here. And on the right-hand side, I can't simplify it. I just leave it as log 9, natural log of 9. And then I add 5 to both sides, and I've got my answer. Okay. So once you get the exponent by itself, you can just take the log, and it brings it gets rid of the base. Okay. Let's see what else we got here. Let me see. Look in the book. We'll just do 2 more problems, I think. Oh, this is oh yeah, well, before we do that, yeah, let me do this. Here's the problem. One thing you can do, I want to point out that there's two approaches to this. This is just like the first one we did when we did exponential equations. One thing I can do is I can just take log of both sides. I can take log base 7. That would make sense. I think that's the best thing to do. So I take log base 7 of both sides. And by the inverse property of logarithms, this becomes x. And I'm done. Got my answer. Very quick. Very quick. I could do something else. I don't have to use log base 7. And sometimes you wouldn't want to do that. If you noticed on your calculator, it's hard to get to log base 7, right? But it's easy to get to log base 10 or log base e. Those are usually buttons right up front. But log base 7 is kind of hard to get to. So a lot of times people will prefer to have log base 10 instead. So if you want to write your answer in terms of log base 10, that's fine. You can do that. Just instead of doing this, do this. Take log base 10 of both sides. This is still going to work because I have the power property of logarithms. Notice I can't cross these out because the inverse property only worked when the bases were the same. Here I have base 10, here I have base 7. So these don't cancel each other out. But what I do have is I have the power property of logarithms. I can bring the exponent out front. Ooh, my pen is getting very gooey. So I can write it like this. X log 7 equals log 43. And now if I want to solve for x, I'll just divide both sides by log 7. So this is probably what you'd do if you wanted to do this on your calculator, because your calculator has log base 10 ready to go. It doesn't have log base 7 ready to go, probably. So this would be much easier to compute. And you can check it. If you compute both of these, you'll get the same answer. If you can get to log base 7 and check it. So you can use any logarithm you want. We could have even used natural logarithm here. That also would have given us the answer. So we don't have to use log base, whatever the base is here. It's kind of nicer in some ways. But but you don't have to. You can use other log bases. Okay. There was the problem that we did at the beginning of class. Let's see if I can find it here. I'm not finding it. It was something like, let me just go back from memory here. We had something like 625 to the x minus 3 to the 125 to the x plus 2 or something. And we had to solve this, right? And so how did we do that? We wrote these with the same base and used the one-to-one property of exponents. Well, we have another way to do this now, right? We can use logarithms. So why don't we just take log base 5 of both sides? Oh, forgot to write log base 5. Okay, well, I can bring the exponents out front. Right, that's the power property. Bring the exponents out front. And now I can simplify these. Look, log base 5 of 625. That's the exponent I'd put on 5 to get 625. That's 4. And what's the exponent I put on 5 to get 25? 125. That's 3. So you see, it also allows us to solve the problem. And we could take it from there, right? Now it's just a polynomial equation that you can solve very easily. There's not even an x squared in there, so that's where this is going to be really easy to solve. Right, so this is another approach to solving that type of problem, just using logarithms. Logarithms will get us to the answer as well. And so whenever you have to get the x, whenever you're solving for the variable that's in the exponent, you can use logarithms to get there. So the last problem I want to look at is an application problem where we will use logarithms to solve an investment problem here. Let me see if I can find a problem like this in the book. Yeah, here's one. Okay, I can just copy this one down. It says Simone invests $8,000 in an account that compounds interest quarterly. Well, yeah, why not? That's what it says. I was like doing continuous compounded interest because it's a simpler formula, but this is what it says. Compounds interest quarterly at a rate of 5%. How long will it take for his money to double? How long for money to double? This is a very natural question, isn't it? This is the kind of thing we naturally want to ask. Like, how long is it going to take for, maybe not double, that's asking a lot, but you know, how long is it going to take for my 8,000 to grow to 10,000 in this bank as opposed to that bank? You know, that's a very natural question. Well, remember the formula for compounded interest. The principal after a certain amount of time is given by, oh, I think they used the word A, the letter A. The amount after a certain amount of time was the principal multiplied by 1 plus r over n times to the power n.
Professor?
Yeah. Oh.
The last statement question. Please read the last piece.
Oh, how yeah, it doesn't make any sense. How long will it take for his money to double? I'm writing sloppily. I'm being shorthand. How much time does he have to wait for his money to double in value? Okay. So thanks for asking, because that didn't make sense. So here's the formula we have for compounded interest. Now, what's the rate? It's 5%. So that means R is 0.05. It's compounded quarterly, which means N is the number of compoundings per year. So N is equal to 4. P is the principal. That's the amount that we initially invested. 8,000. Now, what's A going to be? That's the amount. Well, we want the money to double. So that means A is going to be 16,000. See, he started with 8,000 and we're doubling it to 6,000. And what we want to know is how long is that going to take? What's the T going to be? So let's put all this together. A is 16,000. P is 8,000. 1 plus R over N. Okay, so let's just, I'm going to do this all at once here. So R over N. So 0.05 divided by 4. Okay, that's R over N is 0.0125. If I divide 0.05 by 4, and 1 plus this is just putting a 1 out here. Okay, so this thing on the inside of the parentheses is 1.0125. And then what goes up here, it's n times t. It's 4 times t. T is the only thing we don't know, and that's what we're asking about. How long will it take for his money to double? What is t? That's how long do we have to wait? What's the time? So we just have to solve this for t. Okay? How do we do it? Well, the t is in the exponent. So we're going to use logs. Before we use logs, let's get rid of this 8,000 that's out front. Just like in one of the previous problems, like this one, we got rid of the 2 that was out front. Do that first, all right? 2 is multiplied by the thing raised to the power. So we divided by 2. Same thing here. Something's raised to the power of 4t, but it's being multiplied. Let's divide by that first, okay? So I'm going to divide both sides by 8,000. If I do that, the 8,000s cancel over here, and 16,000 divided by 8,000 is just 2. Okay. Now I'm at a point where I can take logs. Which log do you want to use? Well, we just used log base 10. Let's use natural log for this one. I mean, I could use log base 1.0125, but that's nuts. I mean, I'm never going to find that on a calculator, right? So let's just use natural log. Natural log of 2 is equal to the natural log of this stuff. Why did I take the natural log? Well, because that's going to allow me to bring the exponent down. So the exponent has come out front, which is fantastic because the exponent's got the variable I'm solving for. So now I can proceed to solve for t. So what I want to do is I want to divide both sides by 4, but I also want to divide both sides by log of 1.0125. So do that on the left and do it on the right. We get a bunch of stuff cancels over here, and we've done it. We've solved for t. T equals this, right? Well, this. I'm going to compute it on the calculator, okay? So make a guess about how long you think it might take. And I'm going to go ahead and compute this. Log of 2 divided by 4 times log of 1.0125. Right. So at 5% interest compounded quarterly, how many years would you have to wait for your money to double? Well, I put this into my calculator, and here's what I got. It's not as bad as I thought, 13.95 approximately years. I'm rounding, so I'm going to put an approximate. So about 14 years you're going to have to wait. I thought it was going to be more than that. 5% isn't bad. That's why banks don't give you 5% interest. Nothing even close. they're not going to let you double your money that easily. But yeah, so if you keep stacking 5% interest every year, compounded quarterly, this is how long it's going to take. So this is the power of logarithms. It allows us to solve these kinds of problems, okay? And there's some homework problems that are like this. All right, that is it.
Professor, when
Yes.
you when using the TI-30X calculator, it's in throwing out 3095.
You did log 2 divided by.
Yeah.
Okay.
I
Okay.
use
Now
the
be very
LN.
careful here. If you write on, let me show you something. Okay. Let me. Okay. Let me bring up my computer calculator and show you a common mistake that people make. Can I do it here? Yes. Okay. Cool. I don't know what's going to happen if I share my calculator screen. Let's see. There it is. Okay. Here, I'm going to compute it. I'm going to compute it the wrong way. All right. Here's what I might do. I might do 2 log. Okay, that's the log of 2. Then I'm going to divide by 4 times 1.0125 log. And I get the wrong answer. I get 0.002153. What did I do wrong? Well, I didn't tell my calculator that the log is also in the denominator. What my calculator is doing is it's dividing by, it's taking log 2, it's dividing by 4, it's getting a result, and then it's multiplying that by log of 1.0125. But that's not what I want. I want to divide by 4 times the log. That log should also be in the denominator. So that's what's going wrong here, and that's a common mistake that people might make. So what I need to do, you either need to use parentheses. I think if you can get parentheses on your calculator, that would be ideal. So I do log 2 divide by parentheses 4 times 1.0125 log, and then close parentheses. So now I've got the 4 times log all in the denominator. And now I get it, 13.95. So be very careful with this. Make sure that you use parentheses appropriately. If you don't have parentheses, what you'll have to do is compute the 4 times the log first, write it down, and then take log 2 and divide by that. Right? But if you just string it out in one string of characters, you'll see you get the wrong answer. Okay? So I'm not sure if that was the issue you were having, but I know that's a common issue that people experience when they try to use this calculator for things like this. All right, any other questions?
I got it now.
Okay, great.
All right.
Fantastic. Okay, I think that'll prep you for the homework assignment that we got, 10.5, and that's the last homework. So also keep in mind, I want to show you something very quickly, and then we'll call it quits. Down here, I posted some new videos, all right? So just in the chapter 10 section, there's some very interesting videos here by, he's a really good presenter. He used to be in Khan Academy, but now he does his own, he's got his own YouTube channel. And he does a really great job. His channel's called 3 Blue, 1 Brown, and everything he puts out is fantastic. A lot of it's advanced mathematics, but he's very good at explaining things. But he's been talking about logarithms the last few weeks. So that's fantastic. So if you want to learn a little bit more about logarithms, and he actually explains some of the things that we're talking about, he probably does a better job explaining it than I do. You might check out these videos. Although he goes on and talks about things that are just interesting about them. So he's not like focusing on just the core of what we need to know for our class. So he's going to talk about other stuff. But it's really good to watch. The other thing that I would like you to watch is this classic video from 1977. It's very old, but it's very good. It's still very, very good. And it's about powers of 10 here. And it kind of gives you an idea of exponential functions. So if you watch that, it's really cool. It's only 10 minutes long. Oh, this, I just realized this they probably did that on purpose. 10 minutes long. But that's really worth watching. So if you have some free time, it's easy to watch. It's like a entertaining kind of documentary kind of thing. So I just wanted to point that out. Check those out. Okay.
Professor?
Yeah.
Where you finding the comments on the test? I'm not finding it.
Okay. Oh, let me show you. Give me a second. I gotta open up another browser. Which is taking a long time. Okay. Nope, still taking a long time. There it goes. Where do you? I don't care. Oh man, it looks like this thing just updated, so now it's running all slow. Okay. So here I have my fake student account. So this is what you should be seeing. So if you go into the MyOpen Math, you go to Gradebook, okay, and you can see all the grades that you got on all the assignments. My fake student here didn't do any of them except for one. So you'll notice in here that if something has a little D next to it, that grade has been dropped. So I've dropped the lowest exam grade, and that's what this little D means. Comments. I didn't leave any comments for this fake student, but you would see them in the feedback section here. So if you look in this column, look down here next to exam 1 or 2, you'll see feedback, and it'll have a link. It'll say view feedback. And if you click that view feedback, it'll show you each problem that I gave you feedback on, and it'll show you what I wrote. Okay? So make sure you do that. Please do that, because some of you I left feedback on your exam. I wish it just emailed you, but I guess
I'm not seeing where you're showing.
Well, you may not have any feedback. I mean, if this is blank.
No, I'm not seeing the arrow that you. Oh yeah, now I'm seeing the finger.
Okay, so yeah, these. I don't know if you see my arrow. These cells over here on the far right.
Right.
Right. It'll say view feedback. Here, maybe I can go to another class.
Oh, the picture for you show cutting off the part.
Wait, let me show you in this class here. See, view feedback.
View feedback, view feedback.
And if you click that, it'll show you comments. So I just left very brief comments. No work upload found, right? So that's a comment that some people got, meaning that you were supposed to upload work, and I didn't find it. Right? So if you see that, that's serious. That means I didn't give you any credit for the work that you did because I couldn't find the work. Right? So if you see that and you think it's an error, let me know. Okay.
Okay. All right.
All right. And your grades, your weighted total is right here. This is how your grade in the class so far.
Okay. Keep
track of that number. The final exam, something like 30% of your grade, so it can make a fair bit of difference.
And the date is the 12th, the final exam?
Thursday of next week, so the 21st. And you can take it anytime between 10 a.m. and 8 p.m.
Okay, thank you.
Sure. Any other questions?
How many questions will be there in the final exam?
It's not going to be, I mean, it'll be comparable to, it might be a little bit longer than exam 3, but it's not going to be a lot longer. I'm going to look at exam 3 now just to kind of get an idea. How many did I put on there? 18. Yeah, probably like 20 questions. Okay. Did you find
Same time duration is same, right?
I might
time
give you
duration.
I might give you an extra hour, but expect 3 to 4 hours. I'm going
Okay.
to design it to be done in 2, or I usually design it so that you should, if you know your stuff, you should be able to get it done in an hour and a half. All right, but I'll give you extra time. How was exam 3? Did it seem like it was hard to finish in the time allotted?
Now it was good,
Good.
but now the chapter you're doing, that is little tough.
Yeah.
Well,
Mhm.
you got a week to, I got over a week to figure it out, and I'll be here Thursday to answer questions, and next week you can email me. Or if you need, if
This
you
is
want to
the
set up an
last.
appointment to meet with me in person, I can, well, over Zoom, I can do that too.
Okay.
So if anybody wants to meet with me
I
one-on-one,
didn't start yet the math, that's why I couldn't any question, whatever, because I had another exam. That's why I couldn't start the homework.
okay, but you started it. I mean, if
Only one question I did.
oh, but not all the homework's due yet, right? So you can probably still go in and work those problems, right?
But if any problem, I have to ask. I'm not getting any class, right? This is the last class.
No, Thursday's the last class. We have class
Oh.
Thursday. So bring
Thursday.
questions Thursday.
Okay.
And then, like I was saying, if you want to meet with me online, just send me an email, all right, or message me on My Open Math, and I'll be glad to set up an appointment to meet with you. We can just talk through things one-on-one.
Okay.
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 Any other questions? Okay.
13.95 the years. Should we write it 14 or 13.95 only?
What are you talking about?
The last math. Can we write it 14 or?
The last problem where we got 13.95 as an answer?
Yeah. We should write. We can write it also 14.
I would go, if it was a homework problem, I would actually go to 4 decimal places just to be
Okay.
safe. Okay.
Okay.
With something about years, they probably will let you get away with 1 or 2 decimal places. But just to be safe, I would do everything, all your calculations to 4. That seems to always work in My Open Math if you go to 4 decimal places, just to be safe. Okay, but I'm not sure. Each problem has a different tolerance as to how many decimal places it wants. So I don't know what you can, I don't know what the minimum is you can get away with in a problem like that. Okay, so I'm going to say goodbye, and I'll see you guys on Thursday, all right?
Okay.
Bye.
Bye. See you.
Bye-bye.